Hello, this lecture will cover pages 67 through 71 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Describing Logic Circuits, Part F, DeMorgan's Theorem. We have been using DeMorgan's Theorems all along. We're on page 67 of our lecture notes. Notice there are two laws. You'll recognize this as soon as we get started with it. The first law says x or y, the quantity barred, is the same thing as x barred and y barred. Well, if you take a look at this part of the equation, that's the circuit that tells the story. Make sure you can go from here to here. It's pretty easy. And this is the circuit here. That's the gate that tells the story from this side of the equation. The truth tables, if you take a look, don't memorize truth tables. Don't forget, these are both NOR gates here, just drawn two different ways. This says a 1 here, or a 1 here is the only time you get a low. A 1 here or a 1 here is the only time you get a low, and then by default there's a 1 there. And this one says a low here and a low here is the only time you get a high. A low here and a low here is the only time you get a high. And then by default these are zeros. These are the same truth tables, therefore these are the same gates. That's where we went through that before. But DeMorgan's theorem, when you use it, we have about 6 or 7 examples coming up. Notice what you do here. Basically, you change the gate from a OR to an AND between the two inputs. You invert the inputs, puts a bar above the X. You invert the Y, puts a bar above the Y. And then you invert the whole output, which it's an inversion over inversion. It takes the bar away. That's how you get the equation equal on both sides. The other form for DeMorgan's theorem said that a NAND gate can be drawn like this or can be drawn like this. Basically, here's the truth table proof down here. Make sure you go through that, you understand. But just look at the Boolean expression here. The basic gates and ANDs, you change it to an OR. You invert the input, and you invert the output, which takes it away. Let's go backwards on both of these. Basic gate is a AND, you make it an OR, you invert the inputs, that takes the bar away from the X and the bar away from the Y, then you invert the output and you get back to here. Same thing down here. Make sure you can go both ways, just by looking at the equation. That's DeMorgan's theorem. DeMorgan's theorem basically says a NOR gate can be drawn like this or like this. That's law 1. And a NAND gate can be drawn like this or like this. That's law 2. On page number 68, DeMorgan's theorems can be extended to more than one variable. This takes a little bit of thought, a little getting used to, but here we have an expression that we want to reduce it using DeMorgan's theorem, or just manipulate it using DeMorgan's theorem. Well, in this case down here, I'm just going to work with this side of this of the expression. Notice that the basic gate here is an AND, you make it an OR, you invert each of the inputs, that puts a bar above the A and puts a bar above the B, and it's bar, so B goes just to a single B. Then you invert the whole output. So make sure you can see, we didn't touch the C and we didn't touch the overall bar. We're just working with this part of the circuit down here. Using DeMorgan's theorem just on this particular input to this OR gate. And then we can use DeMorgan's theorem again to go from here to here, but now we're working with that OR gate right there. Change it to an AND, invert this input. Now this whole thing's an input now. It takes the bar away, invert the output, and then you invert the whole thing, it takes that bar away. You have to look at that and work with it. Or you can go this way. I took it this way and I reduced it down. Maybe it's easier to see over here if we go with, we start with this part of the circuit. We treat this as an input and this as an input, and we take that path right there. Here's another example. I did it this way, or I can do it this way. Here's another example. All the examples are on page 68 there, and I did a couple more of them on page 69. Here, use Boolean Algebra on page 69. Use Boolean Algebra to simplify the following expression. I'm using DeMorgan's theorem 2 times. The first time I'm using DeMorgan's theorem at this point. That makes this an input, and it makes this an input. Don't try to use it. Don't try to use it multiple times on one expression. This is going to be an input, and the B bar is going to be an input. So you change the basic gate from an and to an or. You invert this whole input. It keeps the bar above the A here. All you're doing is inverting this input. And you invert this B. B bar goes to a B. Then you invert the whole output. It takes that bar away. So you go from here to here. Now I'm going to use DeMorgan's theorem just on this part here. And you should get down to here. And through law 15a, this whole thing reduces down to just an OR gate. This whole thing is nothing more than an OR gate. A lot of simplification goes on here. This is the way the engineer is going to build it. Save a lot of money. Particularly if you're going to build 200,000 of these in a Ford automobile. Here I simplified the above expression using nothing but gates. I drew this logic expression with gates. Make sure you can go from here to here. Then I just redrew this output like this. I can move this bubble back. If I invert here, if you invert B here and you invert it again there, these will burst one. You get rid of the bubble, right? You get rid of that bubble, get rid of that inverter. So this is gate simplification. You're not going to be responsible for this, but you should be able to recognize how you go from here to here to here to here and get the same expression. This is Boolean Algebra simplification. This is gate simplification. Page number 70. Verify that two-level and/or topology is equivalent to two-level NAND topology. This is used every day by engineers. In other words, a lot of circuits say, for instance, that you want to take A and B or C and D to get an output. Here it is. The output over here is A and B or C and D. By now you should be able to see this as an OR gate on the output, and the two inputs are developed by an AND gate. Two input NAND gate for A and B. The midterm here is AB. And the midterm down here is CD. I didn't write them in. But now what I'm going to do, that's the way I want to implement it. That is called and/or topology. Well, I'm just going to draw this OR gate another way. You know you can draw an OR gate looking like this. And then when you do that, just take this bubble, you can do this on paper, and slide that bubble and put it on here. And slide this bubble back and put it on here. That makes this a NAND gate, this a NAND gate, and this a NAND gate. Basically, you're showing that and/or topology is the same thing as just stacking up NAND gates. Now, it's very convoluted to look at it this way. Look at the output. You look at this output right here and you say, what the heck is that output? Well, that output can be simplified to that. That output can be simplified to this using Boolean Algebra, but I'm using gate reduction here. So in order to avoid confusion by the technician that's working on the circuit, the way I would draw this gate is I would draw this particular gate here another way. These will all be NAND gates. But let me show you what I mean here. This is real important. You want to look this part of the lecture over. Instead of drawing it like this and like that and like that, which is convoluted. If this is A, B, that could be temperature high, pressure high, temperature low, pressure low, where we want to do an alarm. This output right here, Y, is simply going to be equal to A, B, or CD. But you can't see that from here. Very few people can. But if I redraw this output gate, this NAND gate, another way on my schematic for my technician, remember the other way to draw it? You draw it as a negative input OR gate. No, this isn't. Any engineer or technician knows that that's a NAND gate, this is a NAND gate, and this is a NAND gate. They're all three NAND gates. So out of a quad package, you're using 3/4 of one package. As opposed to, if you look back here on this circuit, you need two AND gates, so you're using 50% of a 7408, and then down 50%'s wasted then. And then out here on an OR gate, you're using one of the four on the OR gate, 75%'s wasted of a 7432. You're wasting a lot of gates within the IC package. But down here, this is a 7400 package. You're using 1, 2, 3. You're only wasting 25% if you draw it this way. So when you draw it this way, the technician, when he's troubleshooting it, basically he can burst these bubbles in his mind. If you invert the signal there, invert the signal there, and you invert the signal there, and you invert the signal there, even though this is a low active signal in here, it's not high active, it's a low active signal. But when you're troubleshooting, and all you care about is the input to the output, you can look at, who couldn't look at that circuit and say that is A and B or C and D? Make sure you look this part of page 70 over. It's pretty important. And this is where I explain it here in a little bit more detail. If you didn't get it, maybe you'll get it from my last part of the lecture. Maybe this will be clearer. Here we have to produce an alarm. And the engineer wants to say if temperature is greater than 100 and at the same time pressure is greater than 100, I didn't write a midterm signature in, but that'll go high and you'll put an alarm. Or if the temperature is less than 0 at the same time the pressure is less than 0, you want to do an alarm. So what alarm is equal to here is this and this or this and this. Well, we're wasting two out of the 4 in this package, and we're wasting 3 out of the 4 in this package. But what if we draw these all using NAND gates? I can draw this. I can draw a NAND gate here, a NAND gate here, and a NAND gate here. Draw it like that. Because anybody can look at this and burst those bubbles in their mind and see this circuit up here from that circuit. The only difference is this is a low active signature here between input and output gates. It goes low when you want something to happen here. Up here it went high. But that's just, you just handle that in the troubleshooting. What the technician's concerned is, right here, when this happens at the same time this happens, because it's an AND gate, and this happens the same time as this happens, because it's an AND if you burst these bubbles, and they're ORed together. They look at this, and they see that in their mind. And you know you're going to get an alarm when this happens at the same time this happens, or this happens at the same time that happens. And guess what? You're only wasting 25% of a 7400 package because you're using 3 out of the 4 NAND gates to implement AND OR logic. So, AND OR topology is the same thing as NAND topology. That concludes the lecture.